Alright everyone, welcome back to the second part of this video. This video will specifically focus on beta oxidation. Beta oxidation. So beta oxidation is a type of oxidation whereby fatty acids are broken down, the successive removal of two carbon units as acetyl-CoA. If you remember in the first video, I told you about breaking the oxidation or catabolism of fatty acid into acetyl-CoA. So that's what beta oxidation is about. The process by which two carbon units are removed from fatty acids as acetyl-CoA. So it is a four-step process. Beta oxidation is a four-step process. A repetitive four-step process, because it keeps going. Like, let's say, example of a fatty acid, let's say palmitic acid, right? Two carbon units are removed successively. Two carbon units, because palmitic acid, let me say palmitic acid, it is a 16 carbon units, right? 16 carbon units of fatty acid. But when it undergoes beta oxidation, two carbon units are removed, acetyl-CoA, right? Two carbon units are removed. It will keep going. So let's say we are working with palmitic acid. It will enter the beta oxidation pathway. Two carbon units will be removed. What will now remain is 14 carbon units. That's myristor acid, right? So it will enter the beta oxidation pathway. Two carbon units will be removed again as acetyl-CoA. So you keep going through that cycle over and over till acetyl-CoA has length. So that what I'm trying to say is that if this carbon 16 now, two carbon units will make carbon 14, it will go again to make carbon 12. That's why I say it's a repetitive process whereby two carbon units are removed from what? From the fatty acids. So let me just show you the structure, the general structure of fatty acids. What are fatty acids really? Fatty acids are made up of the carboxylic acid group, that is COOH, and then the hydrocarbon chain that can made from the hydrocarbon chain can be made from 1, 2, 3, 4, from 4 to 36. So this one is a 4 carbon, can keep on going 1 up to 16 or 36. So if it's 16, it's palmitic acid. If it's 14, myristor acid. If it's stearic acid, and so on. So it's made up of the carboxylic group and then the hydrocarbon group. So this thing right here now is the fatty acid. See the carboxylic acid group. See the acyl chain that is made up of the hydrocarbon. You understand? So this thing right here is a fatty acid. So I'm trying to say that in the cells, these fatty acids, they will be oxidized to form acetyl-CoA, whereby two carbon units will be removed from this fatty acid successively, one by one. The two carbon will keep removing. It will undergo the cycle again to remove two carbon till it is completely broken down. You understand? So that's what we are interested in. So this is more fatty acid, right? You can also be written this way actually. You can do it now. You can write like this. Anyway, you can just put it over your put it down, or you can just write it down. Anyway, so you can also write this one, just writing like this. If you understand. Then you can also instead of writing this carbon, you can try to make it like this. Whereby each one here it kind of represents carbon to hydrogen to hydrogen. Same thing like carbon to hydrogen to hydrogen. So these are different from this is the zigzag way of making this, you understand? So you don't get confused. This is the carboxylic acid group. So if you look now, I want to look at this now. This is carbon 1, right? This is carbon 2. This is carbon 3. I can say that this is the carboxylic carbon. This one now right here is carboxylic carbon. Carboxylic carbon. This one now is alpha carbon. This is the beta carbon. All the way down. This is the beta carbon. All the way down to omega. You understand? So beta oxidation occurs at the beta carbon. That is why that is reason for it in a beta oxidation. It occurs at the beta carbon. Let me do a brief recap of what I've just said so far. I'm trying to say that fatty acids, they undergo oxidation, specifically in the mitochondria. This oxidation occurs in the mitochondria of the cells here. So what happens in this mitochondria is a successive breakdown whereby 2 carbon units are removed as acetyl-CoA. If you initially have 14, 2 carbon units will be removed. By the time it goes through that pathway, the beta oxidation pathway, it will now remain 12. 2 will go again plus acetyl-CoA, it will remain 10, and so on and so forth. Alright? So that is what you are, and I read that this thing happens in the mitochondria. It happens in the mitochondria. Fatty acid contains the carboxylic acid group, and then it has the carbon group. So this here now is the acyl chain. Understand? So this is the carboxylic carbon. I can call it the carbon 1. This is alpha carbon. The one that is closest to the carboxylic carbon, the alpha carbon. This is the beta carbon. And I tend to say that the reason they always call the beta oxidation pathway is because oxidation occurs at the beta carbon. You understand? So all the way down to omega. So all these things now, this is acyl-citric. So all these things can be represented as this R, just simple R. So you don't get confused. This R can range from carbon all the, so I'm not trying to say that, so you don't get confused. I can try to write something like this. And then I'll use R to present the rest all the way down. You understand? I can use R to present all the way down the rest of the side chain, the rest of the acyl chain. You understand? So let me now talk about the steps involved before this beta oxidation. The first step is the 1. Activation of fatty acid. The second one is the transport across the mitochondria. Transport across the mitochondria by Carnitine transport system. And then the third one is then the reactions of beta oxidation pathway that occurs in the mitochondrial matrix. So that's the third one. The reactions of what? Beta oxidation. Yeah, that's the third part of it, the reactions of beta oxidation. Let's now talk about the first step, activation of fatty acids. Because this fatty acid, they have to be activated before they can undergo beta oxidation. The reason is because the carbon-to-carbon bonds, they are natively stable. So they have to be activated by adding of a coenzyme A to the carbon 1. That's carboxylic carbon. They have to be. So let me just replace what I'm saying now. This first one will be activation of fatty acid to acetyl-CoA. Yeah. So remember this is the structure of you can write it like this. Can you just write CH2 as 2 carbon here and here, and then this is can you write it like this, or you can write it as like this, same ionized. So this R will represent the rest of the chain. So this carbon bond can go, this carbon to carbon can go on the hydrocarbon chain can go. So this R will represent the rest of the acyl chain. So now I want to talk about the activation of fatty acid, because I feel that the carbon to carbon bonds in fatty acids, they are natively stable. So they have to undergo activation at this carboxylic carbon so that it can allow the beta oxidation at the beta carbon. You understand? So you have to undergo activation. And what it undergoes activation by attachment of CoA to this one. So what will come in here is CoA coenzyme A. You understand? So it will then, this is a fatty acid, right? This is a fatty acid. So it will undergo activation to form what? Acyl-CoA. So let's write acyl-CoA. So I feel that the coenzyme A will attach to this carboxylic carbon. So see what comes here. Let me write like this. That's fine. So this one now has attached here. That's fine. So this thing can also be written out. Can I write it? Let me see. I can try to also write it like this. The same thing, or you can also write this one like this. The same thing. So what am I doing here now? I have activated this fatty acid and converted it into acyl-CoA. Acyl-CoA. So acyl-CoA is just an active form of fatty acid. So this is an active fatty acid. So this activation process, it requires ATP. Yes, it requires ATP. So ATP will go into this, and then AMP, adenosine monophosphate, plus 2 molecules of phosphate, that's the phosphate, it will go out. You understand? So ATP is required for this activation step, activation process so forth. So what do you think will be the name of the enzyme that has this step? What do you think will be the name of the enzyme? This is a fatty acid, this is acyl-CoA. So acyl-CoA is formed, right? Acyl-CoA is synthesized. Understand? So we can call this the name of the enzyme acyl-CoA synthetase. The reason I'm calling synthetase is because ATP was, if ATP was not used in this situation, I'll just call it acyl-CoA synthase. But it's acyl-CoA synthetase. Acyl-CoA synthetase because ATP is required. So acyl-CoA is formed. That's why I'm calling. So the name of this enzyme that catalyzes the conversion from this to this is acyl-CoA synthetase. So with this now, we are covered the first step, which is what? Activation of fatty acid to form acyl-CoA. I think that is very, very important for this to happen so that better oxidation can occur. Yes, fine. So now the next step of the reaction is what? The transport of this acyl-CoA through the mitochondria. So let's look at it. So here's the thing. The first step, that activation of fatty acid, it occurs in the cytosol. Yes. The activation of fatty acid occurs in the cytosol. Understand? But here's the thing. It has to enter the mitochondrial matrix because all these the enzymes of beta oxidation, they are in the mitochondrial matrix. So it has to, that acyl-CoA has to enter the mitochondrial matrix for it to undergo beta oxidation. You understand? But the point is that the inner mitochondria has two membranes, outer and inner mitochondrial membrane. We have to pass, but the problem now is that the inner mitochondrial membrane is impermeable to acyl-CoA, impermeable to acyl-CoA. You understand? So it has to be transported across by a special transport system. So now let's now look at it. Let's look at something. Let's look at something. Let's look at something. Okay. Let's assume that this now is what? The inner mitochondrial membrane that has what's phospholipid bilayer. So phospholipid bilayer is very important. Yeah. This is the inner mitochondrial membrane. Remember that it is impermeable to acyl-CoA. So this here right now is the mitochondrial matrix. So all this is within the cell. This side is the mitochondrial matrix. This side is the cytosolic side. Or this side is the cytosolic side. So it has passed through the outer mitochondria. It's not the inner mitochondrial membrane, but it says that it now needs a special transport mechanism. So see what happens here. The transport mechanism, that's what I will tell you, of course, is called carnitine. Yes, it's called carnitine. So let's say this is how acyl-CoA looks like, right? This is how acyl-CoA looks like. Like this. Let me just end it here. This is how acyl-CoA this is how acyl-CoA looks like, right? But it is that now it has to, it's now so out now, carnitine will enter in, and then this CoA will leave. Right? Yes. So carnitine will then bind to this carboxylic carbon. Understand? With removal of the coenzyme A. So this one now happens. Then binded to carnitine. You understand what was happening here? Carnitine is the transporter that will carry across the inner mitochondrial membrane. So the carnitine will come and bind, we displace this coenzyme A and kind of bind to it. So this was acyl-CoA. This was acyl-CoA. This one now is what? Acyl-carnitine. So what happened was that acyl was transferred from the acyl-CoA, it was transferred to carnitine to form acyl-carnitine. Yes. So what do you think will be the name of the enzyme that applies this? The name of the enzyme is acyl-carnitine transferase 1. Yeah. Acyl. Yeah. Acyl-carnitine transferase 1. Yeah. Yeah. Acyl-carnitine. So the name of the enzyme that we are advertising is carnitine acyl-transferase 1 here. The carnitine acyl-transferase 1 is the name of the enzyme that advertises because the second, there's also a carnitine acyl-transferase 2 that will advertise another reaction inside the mitochondrial membrane. So carnitine acyl-transferase 1, its duty was to transfer the acyl group, remove this one, put the carnitine here. This one is here now. So in this form now, it can then pass through the inner mitochondrial membrane. It can pass through the inner mitochondrial membrane. Yes, to the overlying enzyme or the translocase. This translocase. The translocase. Yes. So this acetyl-carnitine will then pass through like this now. So this acetyl-carnitine, you can see it here. Acyl-carnitine. Yeah. Acyl-carnitine. Yes. So see what will happen here. Carnitine will be another molecule of coenzyme A will enter in. Coenzyme A will enter in and retrieve back this acyl group to itself. So it will enter in and collect the acyl group, forming acyl-CoA. So this acyl-CoA can then go on to form what? It will go on to the beta oxidation pathway to form acetyl-CoA. So this one now is the beta oxidation pathway. That's why see what I'm saying now. So this is characterized by what we can find acyl-transferase 2. Yes. And then this one too will then go back. To then go out. So when acetyl-carnitine is bringing in, is entering this thing, is entering the mitochondrial matrix, carnitine is also needed. It's a co-transport system, right? So when acetyl-carnitine is entering in, carnitine is also leaving out. That will then undergo another transport mechanism to enter back inside. So this is really it. So let's do a recap so far. I said that beta oxidation occurs in the mitochondria. Why? Because the enzymes of mitochondria are found, the enzymes of this beta oxidation are found in the mitochondria. You understand? So it has to get the acyl-CoA that is inside, the fatty acid that is inside the cell, they have to enter inside the mitochondria. They have to enter inside the mitochondria for them to be able to undergo this beta oxidation. So they have to undergo a first step, which is what? Activation of the fatty acid to form acyl-CoA. And the reason for this activation is so that it can become able to undergo beta oxidation because it was initially stable. The carbon-to-carbon bonds in the fatty acid was initially stable. So it has to undergo this oxidation, this activation. So once it's activated, it then has to pass through and enter the mitochondria. That activation occurs in the cytosol. But it has to enter the mitochondrial matrix where all the enzymes are, where all the enzymes of beta oxidation are. Understand? So it's passing through this to enter inside the mitochondria that all this happening. Where carnitine will come and displace the coenzyme A. Carnitine will come and displace the coenzyme A and bind to this form acetyl-carnitine. The acetyl-carnitine can then pass through and enter the mitochondria with the help of the enzyme called translocase. Yes. So translocase, with the help of translocase, it's entered in, and this is the acetyl-carnitine here. So when acetyl-carnitine enters, the coenzyme A will retrieve back the acetyl-CoA. The coenzyme A will come and then take back this acid to form acyl-CoA. So this acyl-CoA is the same acyl-CoA that is here now. So So carnitine is now free to go back. The same time like this one is coming in. So it's kind of it's a co-transport mechanism. So once acyl-CoA is formed, this is the mitochondrial matrix. Inside here, the mitochondrial matrix. This one now can go on to form acetyl-CoA. That's the beta position pathway. You understand? So that is that for this. The acyl-CoA is now in the mitochondrial matrix. I told you that the mitochondrial matrix is where the enzymes of beta oxidation are. So the acyl-CoA is now in the mitochondrial matrix. So it is now ready to undergo beta oxidation. So, beta oxidation is a four-step process, like I told you. The four-step process that includes one is the oxidation by flavin adenine dinucleotide, that's FAD. The second one is a hydration reaction. The third one is oxidation again, but this time by nuclear adenine dinucleotide. And then the fourth one is a lipid reaction, splitting, removal. So these are the four steps of beta oxidation that are catalyzed by enzymes. And that's why that was the whole point of us trying to get into the mitochondria, so that these enzymes will then catalyze these reactions. Understand? So let's look at it. This is our acyl-CoA, right? This is our this is our acyl side chain, the hydrocarbon side chain. And this is this here now is going to be 800 carbon. Yeah. So this is the acyl-CoA. So let's see that in an examiner asks, describe the beta oxidation of a known saturated fatty acid. So instead of just writing acyl-CoA, you can use something like palmityl-CoA. Understand? Palmityl-CoA that has 16 carbon atoms. Yes, you can now say palmityl-CoA. Understand? So this acyl-CoA is a general name for so this R can represent a whole range of carbons. So if it's palmityl-CoA, they know that this carbon has there should be 16 carbon atoms in this as fatty acid. Understand? So remember that the acyl-CoA is the activated form of the fatty acid because of the attachment of a coenzyme E. Understand? So the first reaction I think is oxidation by FAD. So see what happens here. FAD comes in and FAD. So these two molecules of hydrogen left from this. We'll now see how it looks like. Now that two molecules of hydrogen has been removed from this. Two molecules of hydrogen, it will move from here and from here. Yeah. So move on. So now from this. So look at the change. The change happens between these two carbons now. The alpha carbon and the beta carbon. This is the alpha carbon, this is the beta carbon. So what is the change between this and this? The change was that there is now an introduction of a double bond because of the removal of the two hydrogen. Note that carbon has to be bonded to 4 different atoms. So let's count the number of carbon atoms here. The number of the bonds here, you have to have 4 bonds. Understand? So carbon, this is 1 bond, this is 2 bond, this is 3 bond, this is 4 bond. Same time this one. 1, 2, 3. Understand? But now when you don't remove this one, it's now bonded to only 1, 2, and 3. So you have to introduce a double bond. You understand? So there's now a double bond between the alpha carbon. This is the carboxylic one. This is the alpha carbon. This is the beta carbon. So there's now a double bond between the alpha carbon and beta carbon, making it unsaturated. So this is the name of this is actually called alpha beta unsaturated fatty acyl-CoA. Yes. Or another name we can call it is delta 2 trans enol CoA. Why I'm calling it trans because this hydrogen because of the trans double bond between these two carbons. There's a trans double bond. One is here, one is here. Understand? A trans double carbon between, that's why we have called trans-CoA. So this right here now is the first reaction of beta oxidation, and it's characterized by what? It is characterized by acyl-CoA, the hydrogenase. The hydrogenase. This hydrogenase is just to say that hydrogen left. Hydrogen left from this molecule. Hydrogen atoms left from the molecule. So this was acyl-CoA, right? So hydrogen, acyl-CoA dehydrogenase means that the hydrogen molecules left from this acyl-CoA to now form the alpha-beta unsaturated fatty acyl-CoA. I can say trans-enol. Trans-enol, this is that, well, this hydrogen is hydrogen, that's the trans-double bond, you understand? So that's it. This is the first reaction of beta oxidation. So this one now can go on to enter the respiratory chain. You can enter the respiratory chain to give off 1.5 AT. Yes. You understand? So the next step of beta oxidation now is what? Hydration. What does hydration mean? Hydration now means that a molecule of water, H2O will be introduced. A molecule of H2O will be what? Introduced. So H2O will now be introduced. And without, you can even guess the name of the enzyme. This is trans-enol-CoA. So you can call it enol-CoA hydratase. Hydratase because what H2O was introduced, right? Hydration reaction characterized by the hydratase. Understand? So this name of the reaction that will characterize this is enol-CoA hydratase. Yes. From textbook you see trans-enol-CoA hydratase. So okay, so H2 will now come in. Now look at H2 is more like H2 will come in and then it's only OH here. See what happens. Let me show you what happens. So now there won't be double bond again, there won't be a single bond because H2 will enter this at these 2 points. So let me just for the sake of better understanding, let me say this. Let me say that let me just say that the H is here. Why the H is here this one? So I want to just so you understand something better. H2 is more like the hydroxyl group and the hydrogen group. So this hydroxyl this thing will enter here now, while this hydrogen will enter here, and then it will now be saturated because the carbon is now bonded to one. Let me show you what you do. So this carbon here. So this OH from this H2 will come here. This H, this is still it. Understand? This hydrogen here now, this hydrogen here will come here. And then this hydrogen will be right? Then it's CO. Yeah. So what do you think will be the name of this molecule? This molecule will be called, notice that there is a hydroxyl group in the beta carbon. Remember, I know that this is the carboxyl carbon, this is the alpha carbon, this is the beta carbon, and so this arrow represents like the acute chain. So this is the beta carbon now. So this will now be called beta hydroxyl acetyl-CoA. Beta hydroxyl acetyl-CoA. But the most described as beta hydroxyl fatty acetyl-CoA. Fatty acetyl-CoA. This L here is at the left side. It is, if you enjoy it, is at the left side. The OH is at the orientation of the waves at the left side. So, and the beta carbon is where the OH is. That's why we call it the beta hydroxyl fatty acetyl-CoA. Let me do a quick recap. Okay, so I think that the first reaction is characterized by it's an oxidational reaction characterized by acyl-CoA dehydrogenase. You know what is that? What's oxidation? Oxidation is could be removal of hydrogen. So two atoms of hydrogen was removed. This is it. So it's removed from one molecule. Anyhow, from here. The point now is that there is now information of a trans double bond between these two carbons. Yes, trans double bond between these two carbons. Initially, I said it's saturated, now it's unsaturated because of this double bond. That's why we call it alpha, beta, unsaturated fatty acid. You understand? Fatty acid CoA because of this one here. You understand? So, because of this coenzyme here. So now, next step of the reaction is hydration reaction. Hydration, whereby you introduce a molecule of H2O, and from this H2O now, that's two molecules of, that's hydrogen to hydrogen, right? See, this will be here, So this OH now will come and go here. OH will enter here. While the hydrogen will now enter here, making this a single bond again, because carbon wanted to 1, 2, 3, 4. So it's now single bonds again. So these are beta hydroxyl fatty acid. You understand? So what is the next reaction that we want to go? Oxidation by NAD. Oxidation by NAD. Nicotinamide adenine dinucleotide. So see what happens here. NAD. We go in. Oxidation is also a dehydrogenation reaction. This one will be the dehydrogenation, removal of hydrogen. So it's now the removal of hydrogen to hydrogen. So with this, you already know that 2 atoms of hydrogen has to go from this. Yes, two atoms of hydrogen. This hydrogen will leave. This hydrogen will leave. What will now form? Look at it here. Think about it here. Look at what happened here. I think that it was an oxidation reaction, removal of hydrogen. Oxidation reaction, removal of hydrogen. So hydrogen was removed from here, hydrogen was removed from here, forming carbon, double bond to oxygen, and then the rest of it. So this one is, what's the name of this reaction now? It is not, what's the name of this compound now? Beta, keto, acyl. Yes. And the name of this the enzyme that catalyzes this reaction will be, this is beta hydroxy fatty acid-CoA, right? It's not catalyzed by beta hydroxy fatty acid-CoA dehydrogenase. There was a dehydrogenation here because of the removal of hydrogen from here and here, forming a double bond between this. Do you understand? Hydrogen was moved from here and here, forming a double bond. Carbon probably wanted to oxygen to here and here. You know why we are doing all this? Do you notice something? This side is coming to look more like this side. This side here is going to look more like this side. Because we are preparing for this fourth reaction, the cleavage. We are preparing for the cleavage so that there will be splitting. 2 carbon units will be removed as acetyl-CoA. Remaining 14 carbon atoms will go back again and continue this side. Understand? So where would I draw this? Let me continue from here. So the next one is cleavage. So I don't know what I'm trying to do is to make this side look like this side. Understand? But the reason is made is this thing, right? If I were to add this to here now, this side will look like this side. So that's why we can introduce coenzyme A, a molecule of coenzyme A. And then it will be this one, this is a cleavage reaction. So it will be characterized by what? Thiones. Yes. So now see what will happen here. There will be a cleavage at which point? There will be a cleavage at this point. There will be a cleavage at this point here. At this point here. So see what will happen now. So this coenzyme will now enter here. There will be a cleavage forming 2. That's division, splitting, forming this one, and then this one here now. This is it here. So what is this now? So this is the 2 carbon units now. This is the acetyl-CoA we'll be talking about all this while. The 2 carbon units as acetyl-CoA. So do you know that like this now? We've successfully undergone one cycle of beta oxidation. I think that beta oxidation is sequential removal of 2 carbon units. Beta oxidation is the sequential removal of 2 carbon units from acyl-CoA. So this is the 2 carbon unit now, the acetyl-CoA, it has been removed. So remember, we are as beta keto acyl-CoA, and then there was a cleavage here. You understand? And then this coenzyme was introduced to this one. Why the point of introducing this so that it's become so this thing right here now is an acyl-CoA that has been reduced by 2 carbon units. So if initially it was mitochondria that has 16 carbon units, and this one is acyl-CoA that now has 14 carbon units. So this is actually myristor CoA. So this myristor CoA will now go back and restart. Okay, so now go back and restart this cycle over again. Myristor CoA that has 14 carbon atoms will go back and restart this cycle again. It's now 2 carbon units remove from it again. Like this, it will remove from it again as acetyl-CoA and form what? It will remove from it again and form a 10 carbon units. It will go back again through this cycle, form 8 carbon units, go back again, form 6 carbon units with the successive removal of this acetyl-CoA. You might be like, what is acetyl-CoA that is being removed? Where is it going? What is it doing? So this acetyl-CoA right now, it has 2 fates. It can either enter the citric acid cycle. It can either enter the citric acid cycle, a cycle like this. The cycle like this is TCA cycle, the citric acid cycle, where it will generate 10 ATP. It will generate 10 ATP. So this acetyl-CoA, I'm going to say that this acetyl-CoA has 2 fates. It can go and enter the TCA cycle to generate 10 ATP with the release of CO2 plus H2O. Or it can also go as well to form ketone bodies in the liver. Understand? And then the second is that acetyl-CoA, this acetyl-CoA has been sequentially removed from the long-chain fatty acid. It can either undergo a citric acid cycle. This is the TCA cycle by remove CO2 and H2O with the successive generation of ATP. So look at all the places that ATP was generated. FADH can enter the respiratory chain to generate 1.5 ATP. Also, NAD, this one here right now, it can also go to the respiratory chain as well to form 2.5 ATP. Then the acetyl-CoA, if it enters citric acid cycle, to form 10 ATP. So when you combine all this and multiply it by the number of cycles, that's when you then know the energy yield. That's when you know the energy yield of this entire cycle. So that's what I'm saying. Acetyl-CoA, it can either go on to become completely oxidized in the citric acid cycle to yield 10 ATP, or it can go and form ketone bodies in the liver. Understand? It can go and form ketone bodies in the liver. Ketone bodies are water soluble fluids that are exported to brains and other tissues when glucose is not available. Yes. So you see my point now. I see that this acyl-CoA that is now shortened by 2 carbon units will go back again. So let's say something like this now, this mitochondria that has 16 carbon units. How many times do you think it will keep going for 2 carbon units to be removed from it to now be completely oxidized, to now form acetyl-CoA? Like how many times do you think it will go through this cycle? It is 16 carbon units. You might think 8 times, you might think 8 cycles, right? And it's not 8 cycles, it's 7 cycles, because at that 7th process now, what will now remain is a 2 carbon units, acetyl-CoA. Acetyl-CoA is what will remain. So if it's a 16 carbon units per mitochondria, it will only go 7 times for it to form 8 acetyl-CoA. You understand? So let me wipe this. Hope you understood this. I've told you that this is the four-step process of deposition, which occurs in the mitochondria. This is the 4-step process. The first process, this is the oxidation whereby 2 hydrogen atoms was removed from the acetyl-CoA. 2 hydrogen molecules were removed from here. It was removed from here, forming a trans double bond. So hydrogen is here. There's now a trans double bond here now. You understand? Because carbon has to have carbons 1, 2, 3, 4. So if this is now saturated, this is unsaturated now, understand? Between the alpha carbon and the beta carbon, forming alpha beta unsaturated fatty acid, it will then undergo the next one, which is hydration. A molecule of H2 will enter in OH from that H2 will go and bind here, and then H will go and bind here. So this is it. This is what? And this is called the beta hydroxyl. Okay, they are right there on this enzyme. One of these enzymes is beta. One of this enzyme is beta. Let me use it. Beta hydroxyl. acyl-CoA, dehydrogenase. Yes. So this one now is the cleavage reaction, whereby coenzyme A will enter here, so that we can attach. Right now, it's space for us here. So this coenzyme A will come and attach here, so that this one can go, this one too can go. Understand? This one will go and enter the citric acid cycle or enter ketogenesis to form ketone bodies. This one will go and undergo this cycle all over again. Keep undergoing over and over again, right? So that's it. So what I want to talk about next now is energy yield from this deforestation. Energy yield from deforestation. Let's say we are talking about the 16 carbon units, the palmitoid-CoA. What is the energy yield from palmitoid-CoA? What is the energy yield from palmitoid-CoA? That's how many ATP does it generate? How many energy is conserved? How much energy is conserved as what? As ATP. So the first reaction, remember that it was catalyzed by the coenzyme that worked there was FAT to form FADH2, which enters the spaces chain to form 1.5 ATP. So let's say that palmitoid-CoA undergoes 7 using palmitoid-CoA as an example, it undergoes 7 cycles of beta oxidation to form 2 carbon units, 8 acetyl-CoA. You understand what I'm saying? It undergoes 7 cycles to form 8 acetyl-CoA. So this 8 acetyl-CoA, I thought that it can be said to go to the TCA cycle. TCA cycle to form what? 10 ATP. So each acetyl-CoA will enter citric acid cycle to form 10 ATP as well as combination of CO2 plus H2. So I want to say that 10 ATP is formed for each acetyl-CoA. That means the total energy that will be generated is what? 10 times 8. That is 80 ATP. Yeah. 80. 10 times 8. 80. Under so 80. Amino acid phosphate. So also the FADH2, that was 1.5 per cycle. So it's the 7 cycles, right? The 7 cycle, 1.5 per cycle. So 1.5 times 7 is equals to 10.5. So 10.5 ATP will be added to this. You understand? Under one is the NAD. I know that it will liberate 2.5 ATP in the respiratory chain. So another one is 2.8 ATP. You multiply it by 7 cycles because each cycle, NADH is released, which should enter the respiratory chain to form 2.5 ATP. So this thing undergoes 7 cycles. You now do it 2.5 times 7, which should now form what? 17, which should now form 17.5 ATP, right? So this 10.5 ATP plus 17.5 ATP plus 8 ATP now form 108 ATP. Something like 8 ATP, yes. You can see, you now subtract this by, do you remember the activation of, I'm not about energy yield, I want to know the net yield. I'm trying to know the net yield. So 108 ATP now will be subtracted by, do you remember that 2 ATP? You know that 2 high energy phosphate groups were consumed in the activation of fatty acid. So you now minus it by 2 ATP. So the net yield is now 106 ATP. Yeah. This is you have successfully finished the oxidation. There are other oxidation pathways like alpha oxidation, omega oxidation. Those are the minor pathways. The beta oxidation is by far the most common. There are alpha oxidation, omega oxidation. And there's also the peroxisomal oxidation. This will come in subsequent video. The peroxisomal oxidation in the peroxisomes. There's the peroxisomal oxidation. There's also as well the we can also talk about the disorders of this oxidation. We can talk about ketogenesis. Remember when I told you that the acetyl-CoA, it has 2 fates where it can form the citric acid cycle, but it can enter and form ketone bodies in the liver. Understand? So all this will come in subsequent video. If possible, you have a topic I want you to discuss for my next video, and comment on it in the comment box in the comment section. Alright, thank you very much.